Hello, my name is Katie. I'm a researcher at NOAA AOML in Miami, Florida. I actually am employed through the University of Miami, but I'm based at the NOAA facility. And today I'm going to talk a little bit about ocean acidification. So what is that and why should we care about it? So before I get into what ocean acidification actually is, I'm just going to give some background on the pH scale and pH because that's important for understanding ocean acidification. So essentially what the pH scale is it measures how acidic or basic a substance is. So every liquid is either acidic or basic, and this is determined by the amount of hydrogen present in the liquid. So pH actually stands for potential hydrogen. So this reading basically tells us the amount of hydrogen in the sample. And pH, the way to measure it is actually the negative log of the hydrogen ions. So the lower the pH, the more hydrogen ions you have in your substance. So this figure on the right here kind of shows you some examples of acidic solutions and basic solutions. So like battery acid and stomach acid have really high amounts of hydrogen ions. And then distilled water is considered a neutral pH. So you have equal amount of hydrogen ions and hydroxide ions. And then your more basic solutions like oven cleaner and drain cleaner, there's less amount of hydrogen ions and more hydroxide ions. And when we look at seawater, seawater has a slightly basic pH reading of 8.1, and that'll be important in understanding what ocean acidification is and how it impacts the ocean. So now I'm going to talk a little bit about the role of carbon in seawater and ocean acidification. So essentially, the ocean acts as a giant carbon sink. So through natural biological processes like photosynthesis, the ocean absorbs carbon from the atmosphere, or carbon dioxide from the atmosphere. And this is a particularly good thing for us because as humans, we emit a lot of carbon dioxide into the atmosphere through driving our cars or through factories and things like that. So it's actually a good thing that the ocean helps take carbon dioxide out of the atmosphere. But what's happened just over the last couple of decades is the amount of carbon dioxide becoming present in the atmosphere, it's becoming too much for the ocean to keep up with. And that essentially leads to what ocean acidification is. It's caused by the excess amount of carbon dioxide in the atmosphere. And that in turn is lowering the pH of the ocean, which I'll get into that a little bit more. But this diagram on the right here, this is data from one of our NOAA buoys out at Mauna Loa. And it tells you how much carbon dioxide has been in the atmosphere since around the 1960s. So kind of around the start of the Industrial Revolution, we've seen large increases in atmospheric carbon dioxide. And in turn, we're seeing the amount of carbon dioxide in the seawater increasing, and that is in turn lowering the pH of the ocean. So I have a little diagram here that hopefully will help you visualize how this works, because I know it's a lot of chemistry and just a lot to take in. So what are the costs of living in a high CO2 world? So we have our factories that are emitting carbon dioxide into the atmosphere. And when we have all this carbon dioxide in the atmosphere and it's mixing with water or seawater, it creates a compound called carbonic acid. And when we have excess carbon dioxide or excess carbonic acid in the ocean, this increases the amount of hydrogen ions in the ocean. So when we have increased hydrogen ions, we have a lower pH. If you remember back to the pH scale, the more hydrogen ions that are present, the lower our pH will be. And this is ultimately not great for some particular marine organisms. So there's some marine organisms, particularly ones that are made of shells. So that's kind of what my drawing is here, is organisms that have shells in normal conditions. They're healthy, but as the ocean becomes more acidic, their shells actually start to wither away. And the reason that happens is because this carbonic acid that's present in the ocean, it essentially steals the carbonate that is needed for these marine organisms to build and secrete their shells. So calcium carbonate is an important molecule that like clams and mussels and also corals and sea urchins, they use this to make up their skeletons and their shells. And when we have ocean acidification happening, that reduces the amount of carbonate available in the water. So ultimately, these organisms aren't able to survive and grow if they have less carbonate available to them. And these marine organisms need a specific pH range to survive and grow. So even if we're only seeing a decrease in pH of 0.1 or 0.2, that's a really big deal for these sensitive marine organisms. So when we look at coral reefs specifically, coral reefs are incredibly important from a biological standpoint and for humans as well. They're one of the most biodiverse ecosystems in the world, and they provide food and income for many different communities around the world. So when ocean acidification is happening, we're having these carbonate ions decrease, and ultimately these corals can't grow because their skeletons are made out of calcium carbonate. So ultimately what's happening is that the reef can't grow. And this image here is an example of kind of what's happening here. This is taken by a NOAA scientist. On the left here, we have a healthy looking coral, and then just a period of a couple of years later, due to ocean acidification and also increased water temperatures, this coral could not recover from that. So it's incredibly detrimental to coral reefs, and also ocean acidification reduces the amount of carnivorous grazers that we have on the reef. So that's important for the reef as well, to reduce the amount of algae that's present. So the sea urchins and the clams and things like that, they're important for reef health as well. So when we don't have those organisms and the corals can't grow, we're seeing a decreased amount of biodiversity and actually an increased amount of like macroalgae and seaweed, because ocean acidification is actually increasing the growth of that because they're able to photosynthesize more. And then on the bottom here, I just have an example of what happens to a shell. So this was an experiment done at Smithsonian. They exposed this shell to acidic conditions over a 45-day period, and it's just a good visualization to see what happens. In just 45 days, we see significant withering away of that shell. And so I know this is all sounding kind of depressing, but here at NOAA and other organizations around the world, we're doing a lot to really address the problem of ocean acidification. So at NOAA, we have a program called the Ocean Acidification Program. And there's several different goals of this program. So a lot of what we do is just monitoring. So we put out buoys, or we go on research cruises to go and collect data for what's happening in the ocean regarding just basic water quality, like measuring pH and understanding what's happening with climate change and ocean acidification. We also are looking at the biological response of different organisms to ocean acidification. So at some of our NOAA facilities, we have the ability to manipulate seawater, so we can change the pH and the temperature and put organisms into our system and see how they respond when exposed in a controlled laboratory setting. And we're also producing more education materials, so people can become more educated on what's happening on ocean acidification and climate change. And we're also trying to develop more adaptation strategies for people that are really affected by ocean acidification and climate change. So one example of that would be like the fishing industry. If there's a reduced amount of fish or calcifying organisms, that ultimately impacts their livelihood. So one example I like to give for that is the stone crab industry here in Florida. That's a huge fishing industry. And OA definitely impacts those organisms. So that ultimately can impact the livelihood of many people. We also have a program called the Coral Reef Conservation Program. So this program is specifically focused on coral reefs. And essentially what this program is our scientists go out and monitor reefs all over the world, looking at things like ocean acidification and other stressors that impact coral reefs. We're also conducting research to identify potentially resilient corals to things like ocean acidification. So through experiments, we can identify specific genetic strains of corals that could be resilient to these stressors. And we also participate in coral restoration here in Florida and other parts of the world as well. We have coral nurseries where we grow and take these corals and plant them back out onto degraded reefs. That's what we're doing for corals. And lastly, what can you as a non-scientist do to help? So one of the major points that I like to make is reducing your carbon footprint. So this image here shows you all the different things that you can do. I think some of the major ones are just from travel. Travel alone emits a lot of carbon dioxide into the atmosphere. So reducing the amount that you drive, carpooling, public transportation, reducing the amount of trips that you take every year, things like that. And now after today, you can educate your friends and family on ocean acidification and climate change. I think just educating people is really important, especially for people that don't live on the coast or by the ocean. They don't know what's happening. And lastly, you can support organizations and nonprofits that are studying ocean acidification and climate change and things like that. And if you can't support them financially, you could always consider donating your time. I know organizations like that are always looking for volunteers and things like that. And with that, I'd like to thank you so much for your time, and I can take questions at this point.
Thanks so much, Katie. I just learned so much about ocean acidification. I think it's really important to remember that even if it's not in your own backyard, like you're still contributing to it by like driving and creating those fossil fuels. So even if you're living in like Nebraska or anywhere completely landlocked,
Exactly.
it's still your problem because it still affects you at the end of the day as well.
Yes.
And also, wow, I was going to ask a question about, besides coral reefs, what else does OA impact? But you covered all those different animals and even the economy and things like that. That's really huge. I didn't realize that it was such a big issue. So I do have a couple questions for you. I was going to ask about those animals, but how long would it take to bring back pH levels to pre-industrial levels? Can we? Is it too far gone?
Yeah, I think just taking action now is definitely needed. So supporting like local governors and things like that are very supportive of climate change and mitigating that. I think taking action now, we can stop it from becoming worse than it already is.
Okay.
So like in a business as usual situation, the predictions by the year 2100 is that we'll have a pH of roughly 7.8 or 7.7. But if we take action now, we can definitely reduce that for sure.
So how did you get into the marine science field? How did you know that you wanted to get into that? What colleges did you look at? How do you find jobs in this field? Things that our audience, since it's probably high school students, are probably thinking about, getting ready to think about.
Yeah, of course. I honestly didn't see myself becoming a marine scientist. I think I've always had an interest in science, and I always knew I wanted to do something in science. And I think I went to college kind of locally to my house. I wanted to stay home and commute, and I joined the biology program, and I just had some really influential professors that helped me make that decision to do marine science. I took some oceanography related classes. I also have family in Florida, so I visited Florida a lot growing up, and I went to the aquariums down here and things like that. And I think that definitely helped me decide that I wanted to do marine science.
Yeah. And then you go to Rasmus? Do you go to UM?
I'm not in school anymore.
Okay.
I just work at NOAA. Yeah.
That's pretty cool. And then one last question. What is your favorite part of your job? And then what's your least favorite part of your job?
Yeah, I think my favorite part of my job is being able to collaborate with many different scientists. So the great thing about being at NOAA AOML is that we have a lot of different research going on. So being able to talk to and work with scientists with all different backgrounds, I think makes me really excited. And I think that's what is really needed to address the major issues that the ocean is facing right now. And then probably my least favorite part is related to money, of course. Funding for projects can be challenging, and then the time it takes to actually get the money to do your project can take a while. So that gets a little frustrating, and I think that's what I like the least about the job.
I completely agree. I think it's so cool to have so many scientists studying so many different things and being able to work with them and hear about all these different topics, whether it's like ocean acidification or coral biology or hurricane science. It's a great place to work. I really love it. And then, yeah, I agree. Being a marine scientist, it's definitely a field that you go into to work as a passion.
Yeah, for sure.
But it's very rewarding.
Yes, absolutely.
Yeah, thank you so much for this great presentation. And I hope you have a great day.
Yeah, you're welcome. Thank you so much.